You were faster than me.
Yeah, indeed.
So
But
now
I
you
started the room,
moderator.
but
So it's all good. But now you're moderator, which is fine. But if you could also make me moderator, so I can add the link to your paper and things like. So how you do
okay.
that is you click on my profile, and then there is an option on the bottom.
Make a moderator.
Yeah, exactly. Thank you. Hi, Victoria. How are you?
Good morning. Happy to see everybody. Glad to be here.
Yeah, meet Giacomo. I hope I'm saying your name right.
Yeah, Giacomo, but it's good enough.
Okay. So I'm I was going to say good morning, Dr.
Yeah.
Cacciapaglia, but we're calling you Giacomo.
Yeah, Giacomo is fine.
Or can you please say it? Can you please I missed that. I missed the tutorial for your name.
Sorry, for my family name?
Yes, can you
Yes.
please?
Yeah, Cacciapaglia.
Thank you.
So I think the way you pronounced was perfect.
Okay. So yeah, thanks for doing this and for coming here. It's really nice of you to do that.
No, it's a pleasure.
I hope you'll enjoy it. Usually people say afterwards they enjoyed it, but it could be, could be that people are just being very nice. So that's
Let's see. I'll try to be honest, but for now I'm enjoying it. So
Yay. That's our goal. It seems that guests leave happy. Some of them even return.
yes, that's true.
That might happen to you in your future. If we're lucky, I should say.
Yeah.
So how was your morning, everybody? Or afternoon?
Good.
I'm sorry, I'm making a lot of assumptions. We have an afternoon for Caterina, and then where is your morning, Dr. Cacciapaglia?
Well, I'm towards the end of the day here because I'm in Geneva at the moment.
Oh, okay. Oh,
In
beautiful.
Europe.
Mm-hmm.
But yeah, it was a full day, so all went well. And it started with a lot of rain, and now we are finally seeing the sun. So that's a good news.
Okay, same here. I'm in Oregon. So
And Oregon is very early morning. Well, maybe towards the end of the morning.
yeah, it's sort of the end. I mean, it depends on how late your night was. If it's a very early morning,
It
yeah,
could be very early, yes.
yeah. No, it's late morning.
Mm-hmm.
Yeah.
Is this can I just ask, is this archive is this good, this link, or should I share
Yeah, no, it should
the
be
paper on
good. Yes.
physics? Yeah. Okay.
Mm-hmm.
I wasn't sure anymore if the paper was open source, the the peer reviewed version.
Yeah, it should be. I think it should be.
Okay.
But I mean, the version on the archive is the same as the version published.
Oh, it is. Okay.
Up
Yeah.
to tiny differences. So.
Okay. Yeah. Then we can just leave it.
Well, but I guess while talking, I will try to be not too technical. I guess that's also the scope of this event, no?
Yeah. So it depends who's here. Which I remember, I here to ask questions. But since it's here early, I don't think Serena and so on will be here. They will be listening afterwards to your talk.
Mm-hmm.
So it always depends on the members that I hear, how technical the questions will get. But yeah, I think for introduction it's good to stay for a broad audience, so people that listening, so that anyone that's listening can follow. So
yeah, that's perfect for me. Yeah.
okay, great. Yeah, hi everyone in the audience. Thank you for coming. We'll start in around 8 minutes. So thank you for your patience, and we'll start soon. So is the weather now finally summer? And where you are? Does the summer vacation start now or later?
No, well, here in Europe a bit later.
Okay.
I think a bit toward maybe the end of mid-July, typically.
Okay. Yeah, I hear the kids soon start summer vacation. So
yeah, no, for schools, yeah, I think it already started. At least high school and middle school. University as well. We go on a bit more.
Victoria wanted to say something. I'm sorry I interrupted.
Oh, no, you didn't interrupt. I was just thinking back to when I was last in Geneva. It was a really brief time, and I remember that we found a Mexican restaurant and we could get burritos. I don't know why I remembered that, but certain things stand out. But it was beautiful. I really loved walking around that city.
Indeed, it is a very beautiful city and very international indeed. Also, every time I come here, I try some new ethnic restaurant from different parts of the world.
Exactly. So perhaps that Mexican restaurant is still there. Okay.
Yeah, I'll try to look for it.
So what are some of your favorites that you've located?
Last time I came, we found an Iranian, a Persian restaurant. It was not bad. It's somewhere near the lake. But in Geneva is also the first place where I tried Ethiopian
Oh my
food.
gosh.
It was a really nice surprise.
Isn't that so unique and wonderful?
Yeah.
And I agree. We have a lot of Ethiopian restaurants near to where I live.
Mm-hmm.
And it was something I hadn't tried till I was an adult, and now it's something that just needs to happen regularly. It's so delicious, and the bread it's amazing. So do they serve sort of traditionally, where it's all in the center and everybody's using their hands and sharing?
Yeah, that's how they do it. So just served on a slice of this bread that they used to roll and collect all the food. It's a really nice tradition.
Injera. I'm just trying to remember. The bread is called injera. It's so soft. Katarina, have you tried that? She's thinking.
Yeah. Sorry, a friend of mine in school, one of my best friends, she was from Ethiopia, so I ate at her home, like food.
Oh, that's so special.
Yeah,
nice. That's fantastic to try homemade food.
It is. I had a housemate from Ethiopia for about a year, and it smelled so good in the kitchen. But she used the injera in different ways. Sorry, you had a question?
Yeah. My connection is garbage, so my apologies. I have no idea what's actually going on. But is this paper paywalled? I'm having trouble loading it, and I'm not sure if it's because of my connection being garbage.
Sorry, no.
Or because it's paywalled.
No, hi. This is massive gravitons. We're talking about.
Is it
We were having a
paywalled?
presentation.
Is it behind a paywall on Arvix? That's the question. It's in the chat.
Are you on a Mac? Oh, are you talking about the paper? Sorry.
Is the paper paywalled? That was the question.
No,
I can't tell if it's because my connection is garbage or if it's paywalled.
It's a archive paper, so it's not paywall.
Yeah.
Okay,
that's fully
so this is just
freely available.
Nothing is loading for me. I just switched my SIM and my connection is total garbage, so I can't tell.
Yeah, I think the app is also lately having issues and being very slow and unresponsive. So
I think
that
there's
might.
a lot of these like hidden hallway clubs going on. I think a lot of people are missing from the main hallway, and the app is really slow and glitchy right now. So
Yeah, I know. Like,
Yeah.
the room the other day, didn't have too many people because I don't think people can see the rooms. Like, not members of ours that follow us, but like other people.
They seem to come later on, though. They did show up. I think people might have been bringing people. So,
So just
yeah.
to answer back the question about the paper, I just tried the link that has been shared and it works fine. So I was able to download the paper on my phone.
Thank you for checking. I was just
Hello.
navigating back to my screen with the microphone.
Oh.
We're all over the place.
Sorry, also it happens that once in a while I can't hear anything. So I don't know if it's a problem with the application or there's nobody saying anything.
Okay, well,
Just checking.
yeah, thanks for saying something. So in that case, sometimes it's helpful to go off of Wi-Fi. If you have that option where you are. And then, so, yeah, it will happen for me that suddenly everyone is mute. And I go off Wi-Fi. It's a typical thing in Clubhouse. It's just one of the ways that we troubleshoot.
Okay.
Sorry. And then, yes, they were saying there's a bit of overload in the app right now. So it could also just be glitchy for people. But we're going to have a great time anyway. And the non-science society thing I was just saying was that the injera is also used dried and then put in foods. So it was because I had lived with a woman from Ethiopia then. I saw that she used the injera in a lot of different ways, kind of like, just like a grain, just broken up and dried and cracked and then put in different things that were like curries. So I thought that was interesting.
This is going back to the Ethiopian food, I
Yes.
guess.
Yeah, sorry. It was just like this interruption. Wisdom, have you tried Ethiopian food? And good morning, Wisdom, or afternoon.
hey, yeah, I have. I lived in New York for a while. I feel like you get a pretty good sampling of things if you're in New York for long enough. I think Katarina would agree.
Yeah, that's probably the best thing about New York.
Yeah.
Is that you can get anything at any time from anywhere. And relatively authentic, like mostly pretty authentic, I think. I know that I don't know if it had improved the last years, but my Japanese friends told me that the fresh tofu was not as good as in Japan, but I hope somebody was working on that and now it's a little bit better. But there's like maybe tiny things that are not exactly like they are. But yeah, I think mostly it's pretty good.
Hello, Doctor. Thanks very much for joining us. Hello, everyone.
Hey, Jamie.
Yes,
Good
hello.
evening.
Hope
Hi.
you're all well.
And hi, Denise.
Hey, Denise.
Welcome. Thank you for coming.
Hello, everybody.
Oh my gosh, is
Pleased to be
that
here. This is so
luminescent?
interesting.
Is that bioluminescence or just a really pretty photo?
No, you're right. It is bioluminescent algae.
Oh,
I
I love
changed
them.
that for World Oceans Day was yesterday, so
Yesterday.
I was on theme. Plus,
Yeah.
it's really pretty.
Oh my gosh, it's beautiful. So the photo is it looks like a sunset and it's an ocean scene. Looks like it's a bit of an aerial photo, and then the waves are breaking and they're outlined by illuminated yeah, the edges are illuminated, and so it's bioluminescent algae. It's so pretty.
That sounds lovely.
With blue. The algae is sort of a glowing blue, and the ocean is dark, and the sky is sort of yellow. It's so pretty.
That's cool.
Dennis has really beautiful PTRs. Everyone does, of course.
Okay, I think we can start, and yeah, and then let's get into this amazing work. It's so interesting. So, welcome everyone to the Science Society. We are very honored to have our guest speaker here today, talking about his really amazing work. Dr. Now I forgot, Giacomo Cacciapaglia. I hope I said it more or less right. And
Yeah.
let me give you a little bit of information. He's a senior researcher, and he works in theoretical physics, particle phenomenology, and he did his he went to the University of Pisa, and he studied physics there, and then his PhD he did at the Scuola Normale Superiore in theoretical physics, and then he did his postdoc, one of his postdocs at Cornell University, and then later at UC Davis. And he was also at King's College London for a while, and yeah, and he does really interesting research about and his talk today will be about if massive gravitons are good dark matter candidates. But before we get into it, usually Victoria asks a few general questions, if that's okay, and then the stage. Thank you.
Okay, I'm back. I had to go off Wi-Fi myself. I was having that difficulty. Thank you, Katarina. And welcome. Science Society is so happy to have you here, Dr. Cacciapaglia. And so, yes, I would like to ask you a few questions because it's interesting to learn about people's connections to science. And yeah, it will help to carry us into your presentation in a more personal way. So if you can look back through your life, and this can include your childhood, so you choose where, if you can recall a moment or an experience that may have provided the spark of curiosity that has developed into your interest in science.
Yeah, well, I was not prepared for that question, but brings back to some old memories. First of all, thanks everybody for being here with me. I think it's, we'll try to have some fun for the next hour or so. Yeah, so what brought me into science? Well, actually, I have a very vivid memory that goes back to many years ago when I was really a kid, I think probably 5 or 6. I could barely talk. And one of my aunties, she was studying natural science, so more like biology and animals and stuff like that. And I would love to sit in front of her and babbling, trying to repeat what she was studying. So chemical formulas and stuff like that. I think since then I've been very interested in science. And in fact, I wanted to study natural science when I was a kid, and then I turned into physics when I became a bit more adult. That's all my auntie's fault.
Well, thank you to your auntie. we're all grateful, and we'll become even more so as we hear your discussion. And it's always interesting because people have memory to when this happened, and it's usually a really special memory, and often a person is involved, so we share this. And I think this is why we're doing Science Society, because we want to promote interest and love of science. So thank you. And then can you continue? And another theme I hear is is a shift in in concentration or discipline. And so I'm curious how that happened. And also if you can briefly run us through your path from that point up until now to your current research. And thank you so much.
Mm-hmm. No, I mean, the switch was really, when when I wanted to enroll to university, I found actually, well, maybe the main reason is that I wanted to go to Pisa for the Scuola Normale, which is one of the excellence centers of institutes in Italy. And there they didn't have basically biology, so they only had physics, and at the end that's where my choice went. Also because, well, I loved to study physics when I was in high school. And when I was in university, actually at the very beginning, I was very interested by experimental physics. So I really like to put my hands into detectors, experiments, look for particles, going through these pieces of junk that then will reveal the presence of these particles that, of course, we cannot see with our eyes. But then I got also fascinated more and more by the theoretical part of it. So really try to ask questions and find answers just by using our imagination and mathematics and pure calculations. And that's basically what brought me to who I am right now. I guess that curiosity is really what, well, didn't kill the cat yet, but has been driving me on this path.
Yeah, curiosity. And I think, the courage to follow that curiosity or the mentorship or motivation, encouragement, and here you are. So thank you very much for taking us along and that description of what has brought you here. And at this point, you're welcome to launch into your presentation, and then following that, I think Katarina might have mentioned that we can have a Q&A if that's okay with you, and you can just relax and focus on presenting, and it's our pleasure to bring people up to the stage and moderate the question, so you don't have any of that on your plate. So with that, thank you so much, Dr. Cacciapaglia, and the mic is yours.
Okay, thanks. And well, actually, if there are questions in the audience also during my presentation, I guess everybody can feel free to interrupt me and ask questions. I think at least for me, it's more fun to have a more interactive presentation more than just me talking for a long time. But okay, to drop in the topic, so I will tell you something about how the results that we obtained for this paper that has been shared. So it's about dark matter. And so maybe before talking about the actual work we did in this publication, I want to tell you also a bit more about dark matter. In fact, at the end, it all goes back to curiosity, right? Why do we care so much about dark matter? It's because, well, it's something that we have sort of seen, but not directly. So we have a lot of indirect proof that there is some kind of matter in the universe that is called dark because we cannot see it directly, right? But like I will tell you in a minute, there are really a lot of intriguing indirect probes into the presence of this kind of matter, okay, this mysterious object. And for me, it's an incredible situation because I'm very curious, so I really want to know what this dark matter is. So what are the indirect probes that we have? Well, actually the oldest one came from observations back in the 30s, where people were starting observing galaxies. So as you know, galaxies are like, well, a disk made of stars, okay? And if the disk is not, if you're not looking at the galaxy just from the face, so that it looks like a round disk, but really askew, so that it looks almost like a line, you can measure the velocity of the stars, how they move around the center of the galaxy. Now, this is also an interesting point because, stars move very fast, but they are so far and the distance are so big that this movement is extremely small at the end. So you cannot really see how fast they move just by measuring their position. But you can use the Doppler effect, that is basically a change in the spectrum of the light that they emit, to see how fast they go and if they go towards us or against us. Okay. So what people did was to measure all these velocities, and what they realized is that if you only take into account the mass contained by the stars themselves, then the stars that are very far away towards the edge of the galaxies are going too fast compared to what the speed they should have following the gravitational laws, I mean the Newtonian gravitational laws. Another point that made the puzzle even more interesting is that, well, you can even measure further away from the stars, because in fact the galaxies are enshrouded into a cloud of gas. So this gas is mostly made of hydrogen, and the gas is also rotating at the same speed as the stars. So you can also measure the light emitted by the gas, and because of this Doppler effect, so the change in the frequency of this light, you can also measure the velocity of the gas. Turns out that even gas that is very, very far from the stars goes too fast, right, compared to what it should do following Newtonian's laws. So one hypothesis was that, well, maybe we cannot see all the mass that is there in the galaxy. So there is a big component which is invisible, and that's what dark matter is supposed to be. Now, okay, this could be, one can think, okay, maybe there are other explanations. We're not measuring things very precisely. At the end, we are talking about very far away objects in the sky. But in fact, later came another measurement that again pointed towards the presence of some additional matter in the universe. And this goes to a completely different scale. So before I was talking about galaxies, now we're really talking about the whole universe. Now, as you know, maybe you heard about, there is the cosmic microwave background. So what is this? Well, it's some kind of radiation that is present everywhere in the universe. So in fact, maybe you can imagine, I mean, sometimes we think about the outer space as being completely empty. In reality, it's not empty. There is a radiation that feels really everywhere in the universe. And this radiation, it's something has a very well precise origin. It's actually the light that was trapped in the universe in the very early days, when the universe was, well, I should say very early seconds, because we're really talking about just fractions of a second after the Big Bang. So the universe at the time was basically very compact, and it was so dense that light was trapped inside. So it's a bit like, you know, a very dense pancake. You cannot really see anything inside. Even if you shoot light, it will stay in there. Well, it's not really, but that's the idea. At some point, the universe was expanding, the density dropped, and the pancake suddenly became transparent to light. So all the light that was trapped was suddenly released. And now this light has been traveling freely in the universe, being cooling down because of the expansion of the universe. And we see it now just by pointing a telescope to the sky, directly to the sky. Now, why is this interesting for the dark matter story? What's interesting is that if you just look at this radiation and you measure very precisely the frequency, so the temperature of this radiation in the sky, what people notice is that it's not completely universe. So there are some fluctuations that can be measured. They're extremely tiny. They're really 1 part in 10,000. This is actually 100,000. This is the level we're talking about. But the precision of our instruments is such that we can measure these very tiny fluctuations. And if you do a statistical analysis of the distribution of this fluctuation, what we find is that there is a pattern. So basically, it's a bit like there are sound waves that have been trapped again into this radiation. It's a bit like, you know, sound waves that are frozen into this light that comes from the very, very, very early day of the universe. It's really like a fossil, really. That's the same thing, the same idea. But the fossil is a fluctuation, a sound that is trapped in light. Okay. Now, from this sound, we can basically listen to it and try to figure out what the universe was made of at the time when light was set free. Okay. And well, to make the story short, we can basically extract what's the component of different particles that we know in the universe. Turns out that the particles we know were made of, protons mostly, only constitute 5% of the total energy that is in the universe. And there is a 25% that is also made of matter, but they are not protons. Okay. So again, what is that? And it has to be dark matter because, it's a kind of matter that doesn't interact with light. We only see it because it has some gravitational interactions with the rest of the universe. Okay, so this is to tell you, what's very intriguing about dark matter is that we have seen it, in quotation mark, in two very different systems. So if we look at the whole universe, really as a whole, this is a huge, object, the biggest we can observe. And also if you look at much smaller objects like galaxies. There are, of course, other indications, like, if you look at clusters of galaxies, you can also prove that there is some dark unknown matter in the system as well. But we don't know what this is. So it could be anything. The only thing we know for sure is that all the particles we have been measured and we study every day, like in places like where I am now, which is CERN in Geneva. So these particles cannot be dark matter. They cannot fill the universe and account for this 25% budget of the energy. So it has to be something else. Now, this is one of the biggest questions that is still exciting physicists everywhere in the world. What is this dark matter candidate? And this is the main motivation why I basically started working with my colleagues on the results that are presented in this paper. Now, how did we get there? So in the title, you see that there is the word graviton. So graviton is a particle that has gravitational interactions with the rest of the other particles, only gravitational. Now, this is very intriguing because, like I was telling you before, if you follow the story of dark matter, these kind of new particles, they need to have very, very weak interactions. So they cannot interact with light. They cannot interact strongly with any of the standard model, okay? So what's the weakest force that we have seen in nature? Well, that's gravity. Okay, it might seem counterintuitive because we feel gravity every day, we don't feel the other forces, but that's it. If you measure the strength of gravity, it's actually by many, many orders of magnitude weaker than any other force we have been measuring. So why is this interesting? Because, well, we need a particle that has very weak interactions with the standard model, with photons in particular. And why can that be? Gravity. So that's what drives us to gravitons. Gravitons are particles that interact with the strength of gravity. So they might be maybe good dark matter candidates. That's the main idea. Now, it all sounds pretty nice, except that it doesn't work. Why is it that it doesn't work? Well, because you need to produce these particles. Okay? So in order for them to be there in the universe and constitute 25% of the mass of the universe, they need to be produced at some point. Now, if particles have very weak interactions, one way to produce them is the following. While the universe is expanding and cooling down, other particles, like the ones that constitute us, like protons, electrons, and photons, all of those, they collide with each other. And because of these very small interactions of the gravitons, when two, let's say, ordinary particles like protons collide with each other, they have a very tiny, tiny probability to produce some gravitons, okay? Now, this probability is very tiny. And what happens is that once you produce them, as there is no other graviton around, and they interact very, very weakly, they will just stream freely into the universe and remain there, okay? So you have a mechanism of producing a tiny, tiny amount of these particles during the evolution of the universe. Now, the good thing is that the universe has been around for a very long time. We know that the age of the universe is in the billions of years. So there is a lot of time that can be used for these particles to be produced. So you produce them little by little and they get accumulated, right, until today. And today what we see as dark matter could be the leftover of this production of gravitons. Okay, little by little, they accumulate. At the end of the day, they are 25% of the total mass of the universe. Does it work? Well, no. Unfortunately, the interactions are way too weak. So this has been calculated before, and people realized that indeed this is not the case. You can produce gravitons, but the number of them will be extremely small. So not even a fraction of the 25% that we would need for them to constitute a dark matter candidate. Yeah, sorry. Right, so this seems to be completely hopeless, right? So where does our work come in? We come in at this point because we realized one thing that is that was never observed before. So we recalculated the probability for these gravitons to be produced. And one thing we realized is that being gravitons, so having gravitational interactions, they actually interact with mass, right? I mean, this is what we learn in school when we study Newtonian laws. The laws of gravity are always related to mass, so mass interacts gravitationally. Well, this is not completely true because Einstein later came and told us, well, even energy interacts with gravity. But still, mass is what gives a boost to the interaction of gravity with matter. And where is mass coming from? That's the question we asked. Well, as you might know, the Higgs boson has been discovered here in Geneva about 10 years ago. And this new particle is actually called, the particle that gives mass to particles, to other particles. In fact, what happens is that if the Higgs boson is not around, all the particles in the standard model should be massless, okay? And it's the Higgs boson itself that by, some technical means, that means by having a non-zero value in the vacuum, it can give mass to most of the particles of the standard model. Now, what happens is that during the evolution of the universe, when the universe is very dense and very hot, the Higgs is not in the phase where it breaks, where it gives mass to the standard model particles. So there is a sort of transition between two phases. One, very high temperature, when the universe is very hot and dense, where the Higgs is not giving mass to anybody. It's still there, but it's not doing its job. At some point, at temperatures that are very high, but still, not as high as, we are not as close to as the Big Bang, the Higgs switches phase, and then it starts doing its job. So it's really be like this. This is a change in the dynamics of the Higgs itself. Now, when this happens, the interaction of gravitons to the standard particles is increased by the presence of the mass. And by doing an explicit calculation, we realized that this increase can amount to many orders of magnitude. It can be even, if I remember well, 6 or 7 orders of magnitude in the production rate of these new gravitons. Okay, so knowing this, we repeated the calculation of how many gravitons we would expect to see today if they're produced via these gravitational interactions. And we realized that if the gravitons have a mass around 2 mega electron volt, which is about the mass of a few electrons, 3 or 4 electrons, then we can obtain the correct relic density today just by using gravitational interactions. Okay, and this is all due to this increased production after the Higgs starts doing its job. Now, this is also interesting for a more technical reason. I've been talking a lot about the evolution of the universe, right? From the Big Bang down to today. But in fact, the theories of particles, or the theory of particles that we know and that we've been testing a lot in experiment, only reaches up to about the temperature or the energies where the Higgs is doing its job. Okay, this is about 100 GeV, giga electron volt. Above this scale, we know very little. So there might be some new dynamics, some completely different physics that we haven't discovered yet. Okay. So I'm bringing this out to tell you that we know how the universe has been evolving. We can tell for sure, because we know the physics, up to about the energy where the Higgs becomes active. Above that scale, we don't know, we're not sure, because we don't have any direct measurements there, nor any direct constraint. So our discovery, what we found about this enhancement, also tells us that the production of this dark matter is only happening in the time, okay, in the more recent time, where we can control the physics very well. So there are no unknowns that can sort of make the prediction a bit weaker, okay? Yeah, now, there is another point I wanted to touch upon is, well, now that we know that these massive gravitons can do the job of the dark matter, we need to ask another question. What are they? Okay, what are these gravitons? Well, a graviton in general is like the photon. So the photon is the particle that mediates electromagnetic interaction. They're basically what produce magnetic and electromagnetic phenomena, like, you know, light bulb, of course, emits photons. Gravitons are particles that are emitted by any object that interacts gravitational with another one. Okay, so they are the mediators of gravitational interactions. Now, being so, they cannot be massive. Okay, so the massive gravitons I'm talking about, they're certainly not mediators of gravitational interactions. So there need to be some additional particles that are sort of related to gravity, but they're not exactly the mediators of gravity. There are some cousins of the mediators of gravity that acquire mass because of some special mechanism, okay? Now, before concluding and leaving space to the questions, I want to give you an example of how this could happen, because I think it's quite intriguing. The idea is to use extra dimensions. So, as you know, as you can see with your own eyes, we live in a three-dimensional world. Einstein told us that time is a fourth dimension. So in reality, we live in a four-dimensional world. So when I talk about extra dimensions, I'm really thinking that maybe there is a fifth dimension that can be of the space type that we don't see because it's extremely small, okay? Or for some reason it's inaccessible. So where do the gravitons enter the game? Well, they enter because, you know, maybe there is the possibility that me, so I'm made of particles like protons, electrons, I cannot feel the extra dimension because I'm basically localized on a four-dimensional space. And the fifth dimension, I cannot access. Think of a wall, you know, where there's some insects that can only crawl on the wall, they cannot fly. They will spend their whole life on the wall, right? They will never be able to fly through the room. Now, this is the picture. So the wall is a four-dimensional space where we live on, so we cannot see the rest of the room. However, gravity can, okay? And when this happens, besides the gravitational interactions, there will also be some degrees of freedom that carry some energy in the extra direction. And this energy, at the end, is felt as mass by us that are living on the wall. Now, in reality, well, the model we had to follow, it's a bit more complicated. It's not a model with a single wall. It's really a model with three walls. So the idea there is that you can imagine having two rooms that are connected, that share one wall between them. Us, as poor four-dimensional beings, we live on the middle wall. Okay. Gravity, on the other hand, propagates in the whole space. Okay, so in both rooms. And in fact, they are the only particles that can go through the wall where we live. So we feel their presence because they go through our wall, so they also interact with us. But again, like, we cannot probe directly the space that is beyond the wall. Now, why do we need three? Well, the reason is that we have three scales that are very important here. One is the Planck scale, so the scale that determines the strength of the gravitational interactions. So this is a very, very high scale. Another scale is the Higgs scale. That's related to the wall where we live in. Okay, me made of protons. And another scale is the mass of the dark matter. Okay, that has to be 2 megaelectron-volt. It's much smaller than the Higgs energy. So the extra dimension can be built in such a way that moving through the room requires energy. Okay, so there is a mathematical way to build this kind of extra dimension. And finally, what it means is that if you could propagate in the extra dimension, and you want to go from one wall to another, you need to push very hard and put energy in it. Okay, so there is a wall that requires very little energy, 2 megaelectron volt. That's where our massive gravitons live. And then if you want to move from there to us, you need to push the energy up to the Higgs energy. And if you want to go all the way to the Planck brane, where the Planck wall, where the standard gravitons are, then you need to push even further to much higher scales. Okay, so this is a way to sort of construct in a geometrical way a system where these very light massive gravitons appear and have the correct size of interactions with us, because they are suppressed by the requirement of pushing very hard to get to our wall. I think that's more or less all I wanted to tell you today.
Yeah, thank you so much for that great visual explanation, how to visualize the theories. That's I've never heard it in that way. So yeah, that was really interesting and clarifying. Please, if you have any questions, flash your microphones. I see Denise joined us, Dr. Shah, Eric, yeah, and everyone in the audience also. If you have questions, please come to the stage and ask or write in the chat. Yeah, feel free to join us. So yeah, if Victoria?
Yes, thank you. And I also want to add for our guests in the audience, if
Yeah.
anyone has...
Yep.
Oh, can you hear me? I got the red bar. Am I
No, I can hear you
unintelligible?
very well.
Oh, okay, cool. All right, great. Yeah, I was just wanting to invite friends in the audience, even if your question isn't particularly super grounded in science, and you something in this talk brought up element of interest for you. Please feel free. We want this to be inclusive space and encourage your questions. So yeah, raise your hands if you'd like. Otherwise, Dr. Shah, we usually come to you because you've come toward the end. So maybe you have a question and we can get started with you.
So let me say to Giacomo, that was a wonderful share. That was a heavy topic, honestly. I'm just thinking about that and how can I just make my question better. So actually my question was about the tau particle, and I was just wondering how, based upon the model that you just explained to us, and different dimension and changing the dimension, is that possible to have a tau particle or make it in that dimension or not?
Sorry, what particle? The tau?
Yes, tau particles, light, for the light.
Yeah. Well, no, I mean, in the let's say in the scenario I was talking about, this extra dimension, at the end, all the particles, including the tau and all the muon, the electron, they're all localized on the middle wall. So together with the rest of the matter. But I know that in principle one could elaborate further in the model and try to think of, well, models where different particles that have different mass can be probed in different extra dimensions. But I think the minimal situation is just, well, they're all on the same wall. They're all part of the ordinary matter.
So does it still include the proton surrounded? Okay.
Yeah, basically all the particles we know of that we have measured directly, they are on the middle wall. It's only the gravitons that are able to probe the rest of the space. That's the basic version of the model.
So based upon your model, I mean, do you have any further information about data gathering? I mean, I know that, based upon the graviton, it's a possibility of, data gathering and saving the information. I was just wondering, do you have any further, explanation around that?
Well, I mean, in fact, because the fact that these particles, they couple so weakly to us, I mean, it's very, very hard to probe their existence. Because, typically what we try to do when we propose a model with some new particles is to produce them in the lab. So, I mean, here, as you know, here at CERN, they have the biggest accelerator in the world. We're colliding protons at very, very high energy. But then the coupling of these gravitons to protons are very small because protons are fairly light at the end of the day. However, we are thinking with some colleagues to use colliders of some heavier particles that are proposed for, well, the far future. And there might be some hope to produce gravitons at these collisions. I think besides this, unfortunately, it's very, very hard to probe these kind of models because of these very weak interactions.
Do we
There
have any
was a
missing energy? Do we have any missing energy in this model?
Well, if we produce the gravitons, they will give rise to missing energy, yes. But the thing is, it's very, very hard to produce them. In fact, well, what we are thinking about is that, well, I couldn't go too much into the technical part of that, but, when you have this kind of extra dimensions, you don't have only one massive graviton. In fact, you have many, many of them. And the masses they are all multiples of this, MEV scale, okay? But there's an infinite, well, an almost infinite tower. That means that there will be a huge number. If you have enough energy, like we have these colliders, you might be able to produce a lot of these particles, right? And some of them, they will decay, they will disintegrate into photons. So the idea is that, well, you will have some missing energy, but you also have some photons coming from all these heavier massive gravitons. So those heavier guys, they are not dark matter, okay, because they decay into photons. But still, you can produce them, and if we see a continuum of photons, this might be a signature of specifically this model. Maybe we continue because there are so many of them with different mass that you don't see a resonance with well-defined mass for the two photons equal to the mass of the particle.
Thank you.
So I don't know if that clarifies.
Thank you, Dr. Cacciapaglia.
Yeah.
I'm again want to thank you for the language that you used in your talk, because it was so fascinating. And I want to let you know that I'm getting messages from friends in the audience that were saying, even though they were trying to hold on, that they found it really riveting. So thank you. And I love that feebly interacting massive particles. I want to remind people up here to please flash your mics so that we have lots of us, so it isn't a free-for-all, and we can make sure that we get to everyone. So thank you, Dr. Shah, for your fascinating question.
I think
Who is
Jamie. I
next?
think Jamie
Please,
was next.
Jamie, the mic is yours.
Thank you very much. Doctor, that was an amazing talk. First of all,
Thanks.
I was saying wow for all the stuff that I that I could understand, which was very little, and double wow showing all the things I still have yet to understand, which is very exciting. So I'm going to be spending a long time pulling over this to understand this. But since I've got you here, the big question, when I was looking at your paper and I was reading the abstract, it said here you were talking about the discovery of a chiral enhancement and the production cross sections of massive spin 2 gravitons. And I was hoping that you could please explain, because I'm a total layman here, I hope you could explain what exactly is a cross production section of a mass spin 2, and after that, what actually is a chiral enhancement, please? Thank you.
Yeah, well, it's a bit of language. I mean, it's a technical language that we use in in the paper. But okay, so the spin 2 just refers to an intrinsic property of the graviton. So all gravitons, they have spin 2. So if a spin is basically a rotation of the particle around its axis. Okay, so because of quantum physics, this is actually quantized, so it cannot be any number. It has to be an integer of some units. Okay, that's where the 2 is coming from. Just to give a feeling, the photon is spin 1 and the proton is spin 1/2. Okay, so each particle has a spin, and that's just again describing the rotation of the particle.
Okay.
But again, just a graviton. That's the okay. It's a special feature of the gravitons. Now, regarding the cross-section, this is related to the production of this particle. So during the presentation, I was talking about the probability of particles colliding and producing these massive gravitons, right? So when you think of a collision, you can really think of, well, collision of two objects, right? Like if you're playing pool and there are two balls that collide with each other, okay? So the cross-section is literally a measure of the probability of these two to collide. So if you think of two balls on the pool table, the cross-section is really just the radius, so the surface of the ball if you just look at it, okay? Because the probability to hit it is exactly equal to the size of the ball, right? I mean, the bigger is the ball, the easier it is to hit it. So the cross-section in this case is not the actual size of the particle, but it's a measure of this probability, okay? And we use the same name, cross-section, okay? So as you cut the thing, that you look at the section in the direction of the collision, okay? But again, you can translate that cross-section with probability of production of these massive gravitons. And finally, the chiral enhancement. Well, there's nothing but the effect I was talking about. So the fact that once the Higgs does its job and gives mass to the standard model particles, then the cross-section will become much larger. Okay, so we call it chiral because of technical reasons related actually to the spin, but I don't want to get into that.
It's the handedness, so like left-handed versus right-handed.
Yeah, exactly.
Is the convention, mathematically speaking, and there's some machinery that kind of works out that way. But just in general, there's like right-handed, left-handed. The fact that we can use chirality to coax out some of these particles is quite exciting. A recent paper that actually came out, I believe yesterday or very recently, talked about using a rotation while they were already observing one symmetry. So they were applying two symmetry breakings, and they were able to observe the axial Higgs, which is an interesting result because it's like, I think the first time in a long time that we've discovered a particle not in the LHC or something like that. It's more like a tabletop. Could you comment on the nature of the symmetry breaking, or how perhaps applying two symmetry breakings here might or is that something that was already done? Because it's not clear to me, and I'm just curious from that perspective.
Well, I have to confess, I heard about this paper, but I didn't read it yet. So it's on top of my reading list. So I'm afraid I cannot answer this question because I don't know precisely what.
So with respect to the chirality in your problem, what was the nature of the trick? I guess is like, well, if I was asking Jamie's question, that's what I would naturally assume it to be. Yeah.
Yeah, no, I mean, in this case, like you said, I mean, the chirality is related to this right-handed, left-handed. So there are basically two different ways for the spin of the particles to rotate, okay, clockwise or anti-clockwise. Now, the thing is that this is related to now how the Higgs works. So the Higgs couples one chirality to the other. So basically, this means that without the Higgs, the two chiralities are completely independent from each other. So basically, there will be two electrons, one with one chirality, another one with the opposite chirality. The only way to give mass to electrons is to fuse the two chiralities, so couple the two chiralities with each other. And that's exactly the job done by the Higgs. So when we talk about chiral enhancement, it's really due to the fact that there is the Higgs end entering into the process. So the Higgs flips one chirality, transforms one chirality into the other because it couples them, and this is done through the mass generation. Okay, so I hope that clarified
okay.
this.
So I guess the follow-up question is that purely like, so in my studies of quantum mechanics, all of this always just seemed like mathematical machinery, but how it translates to the actual interface or process, or like, I know spontaneous symmetry breaking is usually like the magic word for most of these things, but was there any sort of delay, or was it rather spontaneous in the sense of other observations that we make?
Sorry, I'm not sure I understand the question. So what's the direct observation of this symmetry breaking?
So if we were to take like so if I'm looking at friction on the surface of a table, I can model it as a negative force coefficient. But then when I get into the condensed matter, it's actually like teeth, and then I want to do rigid body simulation. But then I'm still not getting at it because actually it's the electromagnetism, the repulsion. Well, actually, and then we keep going deeper and deeper. Is there a layer of perhaps activity that seems to be kind of driving all of this? Perhaps
Yeah,
suggesting a new model or something like that. But that's kind of what I'm getting at. Like,
I
is there
see.
any evidence, or are you suspicious, perhaps?
No, well, I mean, I have my own preferences. Let me say. So, in the experimental data, we don't know yet. So, for what we know, we cannot be sure what is the dynamics behind the Higgs. In reality, there might be some. For example, I'm working a lot on models where the Higgs is a so-called composite state. It means that it's made of fermions, so it's made of some more elementary particles. I mean, as you know, you're familiar with a proton that is made of quarks, right? So it could be very similar kind of dynamics. And this is one of, well, we have seen a symmetry breaking that is generated by the condensation of quarks. This is something that has been studied on the lab. So my suspicion is that the same might be happening with the Higgs. But unfortunately, we don't have enough data to say anything about that. So we don't know if
Okay,
it's the
cool.
case.
Yeah,
Yeah.
no, that answers my question. I couldn't
Okay.
get it out in a normal
Mhm.
in a normal English way.
No,
So
yeah,
they're
sure.
going
No,
with the
I
phrasing, but
understand.
that's exactly, I think, what I was curious about, and I think Jamie was asking a very similar question
Mhm.
about like these technical statements have like this a rich structure, but
Mhm.
I like hearing the I don't know what to call it, the gossip of of what you might think personally, because that often drives, like, the suspicion of two sticks together to get the banana. Every once in a while you get
Yeah.
lucky. So this is very fascinating. So thank you. David, welcome to the stage, David.
Am I the only David? That would be very rare. Yeah, I am. Sorry. Had to take a quick look. Sorry about that. Giacomo, what
Mhm.
man? This whole conversation has taken me back to one of my most memorable experiences when I was with Neil deGrasse Tyson at some private event,
Mhm.
and I had never heard about this just because I'm not in the physics space. I'm just kind of an armchair Monday morning, wannabe physicist type of thing. But he said, I mean, he shared kind of what was one of the common theories or popular theories is about a gravity leak, that the dark matter is a gravity leak, possibly from a different dimension. So
Mhm.
I really, a lot of this, I really appreciate how the words you use to really help simplify it. Um, as I'm multitasking, it's still above my pay grade, quite honestly. but can you speak to this extra dimensional rationalization, because I think that's I kind of embrace string theory, again, not as a
Mhm.
pro at all, but more as a kind of a couch surfing physicist wannabe to kind of explain life after death and try to have a grander theory about existence, right, and things like that.
Mhm.
So the way my mind has it currently, I kind of I blend or integrate uh, some of these theories, some of these ideas that aren't fully fleshed out, like string theory and things like that, to try to get a sense for this extra dimensional existence that we might have. And then the thing that kind of blows that out, I'm gonna wrap it up right here. The thing that I'm really intrigued with is just some kind of a conceptual approach to this ever expanding universe, and all the stuff that you're studying with regards to dark matter and things like that. So I just like listening to you. If you could kind of take my gobbledygook and just express whatever your thoughts might be, I'd really appreciate it. And keep up the awesome work. And it's really meaningful. Thank you.
Thanks. No, I mean, I also find very fascinating this idea of extra dimensions. I mean, it's actually one of the first topics I've been working on when I was a student. And yeah, I mean, of course, string theory is a very fascinating theory. For me, one issue is that, well, it's very, very hard to probe with experiments if that's a correct theory that describes their nature or not. And the reason is, well, is mostly because we don't have tools that are powerful enough to get to the energies where we should be able to see some effects. Now, hopefully this, dark matter could be one relic of these extra dimensions. And I was talking about this simple, two-room system, but this can be, of course, embedded into a full string theory scenario. Okay, so it's definitely part of that sort of way of thinking. In fact, as you might know, the idea of extra dimension came out of string theories. There's not some, well, to be completely honest, it's something that people thought this might be surprising back in 1905. So the first papers that talk about extra dimensions, they are very, very old. They are for more than 100 years ago. But then when people discovered string theories, then they realized that they need extra dimensions in that kind of scenario. Then this revived all these explorations of extra dimensions. And I think we're not done yet. So what I find very interesting is that there's a lot more to explore that we have seen so far. Fortunately, it's not only exploration for the mind, because we don't have data that can allow us to check if these ideas are realized or not.
Yeah, but I think that's a testament to theoretical physics in general. It's always amazing that you can take something from the imagination, which is not reality as we see it in laboratories, and make extrapolations. That always kind of blew my mind. I felt like it was like a modern day magician or wizard, that you have some secret codes or something. I guess maybe a tangent question, one that I often ask is, if students were listening to your talk, and they wanted to follow the work, what would you recommend to them? Because from my history, when I started studying string theory, they said, make sure you also study simulation so you can get a job later. So that was very good advice. But in terms of this kind of work, is there a book that you'd recommend, or maybe there's a summary that you recently stumbled upon? So for people who want to dive right into this and not necessarily in the deep end, they start in the shallow end.
About string theory, no, not really. I think, sorry, I don't have anything to recommend.
No, I meant like for your work. So like in my experience, the string theorist said, don't study string theory, do simulations. Here, if you were like students that are working with you now, are they tackling a different portion of the problem compared to what inspired you to tackle it? Like, is there something that is fascinating or annoying right now that you think is something that perhaps people should look at more?
Well, yeah, I think one thing I would tell to my students is that, well, don't do string theory to begin with. I confirm that. Do theoretical physics, because there are a lot of open questions that we still don't know the answer to, like dark matter, like what I was talking about today. But I would also tell them, try to open your mind and see if what you learn to studying physics can be applied to other things. Because I was talking to some colleagues this morning actually about this. At the end, physics is not only about thinking about problems, come up with mathematics, study experiments. It's really solving problems. So that's what I do every day. Basically, I think of a problem, I try to find the best solution for the problem. This can be done for just theoretical problems, like mathematical problems. Can also be done for problems in the real world, let's say, that are more relevant for the society. Let me give you an example. When COVID started, I started working on COVID. So I used basically techniques that I've been using in theoretical physics to study particles, to also study how this COVID has been spreading. And now it's a big part of my research. And I think this is certainly much more useful directly with the society than, come up with theories and versions of string theory. Of course, I mean, this is not to, don't misunderstand me. I'm not saying that theoretical physics is not useful. In fact, one thing that we should always remember is that, I come up with a theory, experimentalists come up with the experiment to probe these theories, and this also implies a huge technological advancement for the whole society, not only for, fundamental science. So there are direct benefits coming from the fact that we try to push the boundary of technology, right? Because we need to find an answer to these questions in the experiments. But there are also ideas that can be used in other fields. So there is a double benefit, right? And I think it's the time we start doing both. That's what I would tell my students.
Yeah, that's awesome. That's very similar to the kind of advice that I got. That the mathematics of string theory, very useful. You can do lots of stuff. And now
Yeah,
I
yeah.
work in biophysics, and again,
Oh,
I also
fantastic.
work in coronavirus rapid detection with a sensor. That's kind of my little startup here. And it was because my professors pushed me to also have these other skills in addition to the fancy mathematics that comes with particle physics. So definitely nice to hear that.
Yeah, thank you, Eric. But also, we are here at the Science Society and it's all about curiosity. So I don't, I'm not sure, but I don't like the idea that science has to have a purpose other than curiosity. Applied sciences are not necessarily good science. Good science is good science. And what comes
No,
out of
but
it, I don't know.
sorry, I mean, just to clarify, I mean, it's
No,
not a purpose. It's part of the curiosity. When I was mentioning some work I've been doing on COVID, it all started from curiosity. We were looking at this data coming in, the number of infections, and the question was, well, why are they behaving like this? And why do they look so familiar? So it all started from curiosity. And then, well, there are also some results that can be beneficial for the society. It's a side product, which is also very important.
oh yeah, I didn't
But
want
it all
to.
starts with
Yeah,
curiosity. I'm totally agree with you.
no, I didn't want to contradict what you're saying. I just wanted to remind that it's really hard to give people advice what they should do with
Yeah,
their
yeah.
life. So
May
I
I?
don't think
Oh, sorry,
anyone can.
Katerina. Sorry.
I don't think anyone really can. So I like that you follow your curiosity, and I
Yeah.
think staying with that message is pretty, because that we never know where it leads. So I think, yeah. So
I would like to interject here because this was going through my mind as well. I'm looking back I took notes. I always take notes at what you had said. And Dr. Cacciapaglia, you were talking about at uni, you were so interested in experimental physics and you loved looking through particles. And then from that, you wanted to try to ask questions that use the imagination. And so I was thinking again, maybe we just have to walk this path that's guided by our curiosity,
Yeah.
and not by the intellect. And this is what it sounded like to me had been your motivation.
Yeah, no, definitely. It has always been my motivation. Exactly. You read it correctly.
Speaking of curiosity, can I throw in another question, please? Because there was something I was hoping some more understanding about. Is that okay, Doctor?
Yeah, sure.
You were discussing this idea of the four dimensions, right? And you said like you imagined like was it like a floor space, yeah, with a wall in the middle.
Yeah.
And you said, are we like the flies where our limit is the wall, right? Or
Yeah.
did you say we lived in the wall, or we were one half of the space? Oh, I wasn't sure if I understood that part.
No, I mean, in the picture, I was really thinking that the particles we are made of are really confined on the wall.
Okay.
So, yeah,
And
just stuck on the wall.
right. So the whole floor space then, this is because these particles, right, the gravitons and stuff, gravity exists in the whole floor space, but we can't access the whole area. Is this is this? Do you think that dark matter then is? Please forgive me if I'm asking a dumb question.
No.
It's difficult to get my head around dark matter. It's a weird concept for me. Is dark matter what's existing in that other wall space that we can't reach?
Yeah, well, that's a possibility. In fact, the model I've been studying more or less falls into that category. So they are really particles that are not completely stuck on the wall, but they need to live very close to the wall. That's what we say. So they are nearly localized. That's more technical words.
Right.
That means that somehow it's very painful for them to reach the wall where we live. That justifies why they interact so rarely with the ordinary matter.
Right, and this is
so definitely, yeah.
And this is then saying that the particles that are that are coming through to us from the other room, is this like the matter that we share with dark matter? But it isn't dark matter, but it's particles that we share with them?
No, it's not really shared. It is the actual dark matter. So the thing is that dark matter can go through the wall where we live and interact with us, but this is very, very rare. It's really a direct interaction between these particles. So I don't know if if it's a correct way to imagine, but you can think of these particles as just floating in the room, and very rarely they hit the wall, right? And that's where we are, on the wall.
Thank you very much for indulging me, Doctor.
No, you're very welcome.
All right, flash of mics. Who is next?
Yeah, I would like to ask a question about when when it was introduced that you think, or the theory basically explores if the dark matter was basically mostly produced during the very early stages of the Big Bang. So, and the reason is, can you explain for me again why exactly only then, or do you expect that there is still some dark matter being produced, maybe in massive black holes, or maybe not?
Yeah, well, I think the key there is the density. So, as the dark matter is produced by particles colliding with each other, okay, and then because of this cross-section I was mentioning, the probability to produce the dark matter, the universe was very dense, very close to the Big Bang. And then because of the expansion, the density has been dropping a lot. And so the probability that two particles find each other in the universe is much smaller today than it was back, very close to the Big Bang. And that's the main reason why the production is mostly happening in the very, very few fractions of seconds of the life of the universe. Now, you are right that there are dense places today in the out there in the space, like black holes. But the problem is that black holes, they are so dense that nothing can escape them. So even if say that dark matter is produced inside the black hole, it will never come out of it. So at the end, it is as if it's not produced. Okay, there are other dense objects, but they're very few again. So
sorry for asking this question, but is there any point in time that also a black hole would die, basically, and transform into something else? Or is there no such thing, basically? I'm sorry for this question.
Well, no, absolutely. As far as we know, no. So they will always be there.
Oh, wow.
These are
Really?
big
Is
ones.
that the only thing that lasts forever? That's really funny.
Yeah, well, if the universe lasts forever, then they will too. But
yeah. I mean,
there
as
is
long
this
as the
theory, the Big
universe
Crunch, where
yeah, that's
but,
so
yeah.
interesting
So,
because
sure.
Religions come up with heaven and things like that, but the actual endless thing that we actually know of is a black hole. I think that's I'm sorry, that's very funny to me.
Speaking of that, I'd actually like to ask about what I saw in your paper, primordial black holes, which sounds so awesome. And is that like, it did say that there's a lot of the physics you don't understand about them or something? Please correct me. at any point. But is it the theory behind primordial black holes is that they weren't created by the same way that we understand black holes to be made now, and that's what is maybe created by a weaker force or something? Can you please explain anything you can about that, please?
Yeah, no, indeed. I mean, let me say it in this way: the different mechanism is that black holes now, I mean, the ones that we think that they come from matter that collapsed, so maybe stars that at the end of the revolution they became so dense and heavy that they just collapse into a black hole. So, but basically, it's matter that becomes so dense that creates a black hole. For the primordial black holes, the difference is that, they're still made by the same physics, let's say, but they're not made by actual particles. They're made by so-called quantum fluctuations. So to give a feeling is the fact that, in quantum physics, just empty space is not empty. So it's just made by, production of particles that are produced and disappear continuously, okay? So those are what we call quantum fluctuations. Now, the thing is that if the universe expands very fast, these quantum fluctuations get basically frozen and expand, so become huge in the universe. Okay, and this is what is thought as the possible origin of these black holes, because their fluctuations, they might become so big that at the end the density of energy contained in them becomes so big that they collapse into a black hole. So somehow they're not real particles that do that. It's some quantum weird stuff that creates these black holes.
That is so incredibly cool. But there's a lot about that we don't understand then that you're saying, right?
Yeah.
This is just like a theory at the moment, like a vague sort of idea at the moment. Yeah.
Yeah, that's a problem. That it's an idea, but it's very hard to really calculate things very precisely or know exactly what's happening. So
right. And was this why you weren't discounting this as a possible candidate for what you're talking about? But
well, no, I mean I wouldn't discard it, but it's a bit hard to believe to think that this is a viable candidate before we can be sure, to be able to calculate how many of these black holes are produced and if they're produced enough to give the 25% of the mass that I was talking about.
right, we need to know better how it works to know if it's
Yeah, I think
actually really
we need a lot
viable.
of progress in the theoretical understanding of the process before we can be sure.
Absolutely. Thank you very much. Primordial black holes. So cool. Okay, thank you,
Yeah,
Doctor.
but I mean, still a viable possibility. We shouldn't put it off the table.
Thank you.
Yeah, we talked a little bit over an hour, so if anyone has some last questions, please flash your microphones. Victoria, did you want to say something?
Thank you. I'm sorry. I don't know if Gilbert had a chance yet to ask a question, and maybe I just missed my screen at that time, so I was just offering it to you, Gilbert.
Oh, thank you very much. I came a bit late, so I don't have any questions. I was just listening in.
Always so happy to have you here.
Okay.
Thank you.
Yeah, thanks for coming.
Thank you, Doctor.
Hi, Alex. Oh, I'm sorry.
Yeah.
Go ahead, Gilbert. Sorry.
Yes, hello. Hello, Katerina. I came in a bit late too, and I have a quick question.
Yes, please go ahead.
Yeah.
We aren't hearing you. Are you able to unmic, Alex?
Sorry about that. Yes.
Oh.
Thank you, Giacomo. Very interesting subject. Are you able to propose any new experiments or an experiment to test your theory?
Yeah, like I was mentioning briefly, we are still working the details, so I'm not sure yet if it can really work. But the idea would be to build a collider using some heavier particles, for example, muons. I think this is a big technological challenge, but it might lead to enough production of these new gravitons that they can be actually detected. But this is really work in progress, so we are trying to estimate if this is a viable possibility or not.
And how would you actually detect them? Like, what sort of a detector would you need?
Well, actually, detector is just a standard detector that is being used also today. Because what we need to detect is either the fact that we produce particles that then escape, because they are like dark matter, so you don't detect them. So you need to detect all the rest, right, to see these missing particles, or some heavier graviton that then decay into photons. So we need a detector that can detect photons very efficiently, even photons with a very small energy. But the problem is really be able to collide muons. That's the hard part.
I see. And is there any possibility to adapt the LHC to do that?
No, I'm afraid not. And in fact, the LHC is a collider of very, very light particles. So unfortunately, it will not do the job for us. Because it collides quarks and gluons that are basically massless.
So would the place to make those kind of observations just be like from cosmic rays, I guess?
Yeah, there might be something there too. And it's something we are starting to explore right now, if there is any way to see them indirectly. Or directly, from cosmic rays. But the problem is that, again, the couplings are so small that at the end it's very, very hard to produce them. It's a big challenge.
Can I also ask you, I don't know if this is like a basic physics question that I haven't touched on yet, but the electroweak symmetry, sorry, I'm trying to get the name of it here. I've wrote it down. The electroweak symmetry breaking scale. Can you explain what is that exactly? That sounds really interesting.
Yeah, well, that's the scale where the Higgs does its job. That's how I described it during the talk. Because in fact, I mean, the Higgs is the particle that gives mass, right? But the thing is that it gives mass by breaking a symmetry, which is precisely the electroweak symmetry. So this is related to the issue of chirality that we touched upon before. So the fact is that the left-handed one chirality of the standard model particles coupled to the electroweak particles. The other one doesn't. So the only way to connect the two is to break this electroweak symmetry. I'm simplifying a bit, but that's the essence.
Oh, no, actually, sorry, that's really helpful. Sorry if I didn't pick up on that in the talk before, but this definitely needs me to read a lot more about this. This is actually quite fascinating. Yeah, thank you.
No, I didn't mention electroweak, so it's a good question you asked. They're all connected at the end.
Thank you so much. This is amazing. This is so exciting. This is amazing. Thank you.
I see that Nope in the audience has a question, but I'm having trouble to bring you. Oh, now it worked. Hi, how are you? Welcome to the stage. Please ask your question.
Yeah, thanks. What an awesome look was. I just wanted to ask, can graviton be considered a fundamental particle?
Fundamental? Yeah. You can think of it as a fundamental particle. I mean, if you think about this extra-dimensional scenario, then definitely it is. Of course, one can also think of it as a composite particle. I mean, in that case, it will be a bit like, a glue ball or something made of some other particles. This is definitely another possibility. I think probably being explored in the literature. So both ways is viable. I hope that answered the question.
Yes, thanks.
Okay, thanks.
Yeah, thank you so much for taking the time. I know we've taken up a little bit more of your time, more than an
That's
hour.
okay. So I was very happy of the many questions. That's great.
Yeah, and so we are very thankful that you made the time and that you came and presented this work. It's such a fundamental questions that you're answering with your work. So it's always so interesting to hear where we come from, how our universe was built, and I feel like we have to learn so much more about it in the general public. So yeah, it's really important work, and thank you for sharing it with us.
I'm personally hoping you come back sometime in the near future, Doctor, because I'm going to read through all this and have lots more questions for you. There's just so much that I don't understand, but I can tell this is mind-blowing stuff. So I really, really hope I get a chance to speak to you again. We all do. Thank you so
Yeah,
much for
definitely.
being
Looking
here.
forward to it.
Yes, thank you, Dr. Cacciapaglia. I hope that's your take-home message, that you came and found a very receptive and extremely enthusiastic audience. So
Yeah,
lots of
definitely.
appreciation.
Yeah, thanks you all for staying with me for so long. It was fun.
Yeah, and yeah, you're welcome anytime to come. And thank you everyone for coming and asking questions and for making our guest speaker feel welcome. And yeah, I hope we'll hear you again sometime, not see you. And and yeah, this was a wonderful discussion. Thank you, everyone, and of course, a special thanks to you, Giacomo. So,
Okay, thanks.
if you like discussions like this, follow the club. Maybe we get the chance to talk about these topics again. We have later in the evening Dr. Moses talking about the BCI work, where it decoded speech and paralyzed people. And was I gone for a second? I feel like
No.
No,
oh
over here.
yeah, the room was gone for a second for me. That's my and
Dark
yeah.
matter.
I don't know. Lately the app is kind of good. Yeah, so feel free to come back, follow the club, follow Dr. Giacomo, and thank you everyone. I'll close the room in 3, 2.
And Doctor, we wish you all the funding and all the
Oh right,
best before we
yes.
see you next
Okay,
time as well.
thanks.
Thank you so
No, it was
much.
really great. I'll definitely follow the activities of this club.
Please do.
Yeah, thank you so much.
Okay,
Okay,
bye
3,
everybody.
2,
Have a good
1,
day,
bye.
everyone.
Bye,
Take
bye
care,
bye.
Doctor. Thank you. Bye bye.